Hey guys, Greg here. Today let's talk about two important data structures, namely heaps and priority queues. And let me just get this out of the way right at the beginning. These two things basically mean exactly the same thing. Whether someone says a heap or a priority queue, they're really referring to the same data structure. Okay, so a heap or priority queue is actually a particular type of binary tree. Now I'm going to draw a binary tree, although it's not going to be a heap quite yet. Okay, so this is a binary tree, and let's remember that you could actually represent this as an array. And I'll actually do this a little differently than I did the first time. We'll use the first index, and so this is going to be the root, which is 2, and then we'll have the next two children, 5 and 0 here, so this will be 5 and 0 at positions 1 and 2. And then in general, the formula is that for any index I, its left child, if it exists, will be at 2 times I plus 1, and its right child is going to be 2 times I plus 2. So let's just fill this out here. You would have it in a line, so this will be 1, then 10, then 8 and -4, and the last line will be 3 and 12 and 9. Okay, so what this formula means here is, say we had I is equal to 3, well that would mean we're referring to this node with a value of 1. So we're talking about this node right here. If you wanted to find its left child in the array, well then you would do 2 times I plus 1, so that is going to be 2 times 3 plus 1, which is going to give a value of 7, so that gives the array position of its left child of 3. So that shows you that its left child is going to have a value of 3, which indeed it does. If you added one more here, so 2 times I plus 2, that's going to give a value of 8, which is where its right child is, so that's going to have a value of 12. We can see that that is indeed correct. So using this formula and any position in the array, we can find the value of its left and right child. Now this tree is not a heap, okay? This one right here, this is definitely not a heap. It is a binary tree. Now a heap is a particular type of binary tree that has a certain property. And there's two versions. There's either a min heap, which is good for finding the minimum, or there's a max heap, good for finding maximums. Now to turn this into a min heap, you would use a function called Heapify, or more specifically min Heapify. Okay, so this is still a binary tree, but it is what you would call a min heap. So the minimum element is at the very top, so the root node is going to be the minimum. And then it also has the property that if you pick any node, so say this one, well that's going to be smaller than both of these two. And if you pick this node, well then it's going to be smaller than both of these two. So with this arrangement here, if you wanted to pop the minimum value off, well you would have to do this. It would be called a heap pop. You would take that -4 out, and then the tree would have to fix itself. And so we'd have to decide which of these two we'd want to promote. Well, we don't want the 1 because that's actually bigger than the 0. We'd want the minimum up there. So we would promote the 0 up here, but now this is broken over here. So we'd have to get the smaller of these two values, so the 2 to promote. And then if there was 2 here, you'd pick the smaller one, but we pick the only one that's there, which is the 9. So notice we just popped off the minimum and we did an operation going down the tree. So we basically just took one path down the tree. And so whenever you do stuff that's in relation to the height of the tree, as long as the tree is roughly balanced height-wise, it's going to be a log base 2n operation to go down that path of the tree. That is an operation which we'll call heap pop, and that has a time complexity of O of log n, because you just have to fix that one path of the tree by promoting up the smaller one. It just takes log time to pop off the minimum, so heap pop is basically just an extract min, so that's the main purpose of it. You can do that in log n time repeatedly. So heap pop, or basically extract the minimum, that's going to be a log n operation. It basically just takes the minimum, it pops it out, it would return that to you, and it's going to fix that tree in log time. Oftentimes you would want to insert a new value into the heap, so you can do insert, or what I'll just call as heap push. So if you push something into the heap, this, as we'll see, is also going to take big O of log n time. Let's think about this as inserting a 7. So basically what it would do here is it would make space in the array for the 7 over here, and we'd basically just keep asking, are we happy with its position? Well, we're not happy with it here because it's smaller than the 9, and so the 7 should actually be above the 9. We'd swap those two, and so it's going to put this down, and the 7 is going to go up, and it would say, are we happy with its position here? Well, yes, we actually are, because it is bigger than the 2, and so we found its correct spot. Now let's do this again, say inserting a value of 13. So if we try to put that in there, well, it'll say, okay, let's make some space for it here. Are we happy with it there? Well, yes, actually we are, because it's going to be bigger than that value, and that's what we want. So we're happy with it. Let's do this with a value of -2. So if we try to put this in there, okay, are we happy with it here? Well, no, it's actually smaller than the 10, and so we'd rather swap these. We're not happy with this, so we would swap the -2 with the 1, and we would actually end up swapping with the root as well. And then of course there's nowhere to go from there. So again, notice we're basically just doing swaps all the way up the tree. In the worst case, we're just climbing up this whole branch here. And so again, you're doing a branch of the tree, which is basically a log base 2 of n. And just to explain why log base 2 of n makes a lot of sense here, if you had n nodes in the tree total, so if there was n nodes here, say if we started at the beginning here and we went down the branch like this, well, if we were at this step, well, if you went left, you're basically saying I'm not doing half of the total tree. You then get over here, and if we go down here, you're saying I don't want half of the remaining tree, and so you go down here. So basically what's happening here is that you keep repeatedly dividing n by 2, and so whenever you do something involving a branch, assuming the tree is roughly height balanced, then it is going to be log base 2 of n. Something very simple you might want to do with a heap is called a heap peak, which basically just means ask what the minimum is, and so you can do that in constant time, because again, if this was represented by an array, well then the first position is going to be the root, and so you really just ask like, okay, what is the array at 0? That's a very quick operation, but it is quite useful. And just to quickly explain why heaps and priority queues are really the same thing here, what a priority queue is basically just saying the people with higher priority will go first. So, you know, celebrities and people of royalty are going to be more important, they come out of the line first. And so if you have the person with, say, the most priority, which is person A, they have the highest priority of 1, or the lowest value. If we had person B, which is slightly less important, at 2, another person of 3, well, it's basically just saying we want the person with the smallest number here to be processed first. And that's exactly what this is doing. It's processing the things with the smallest value. Now, all of this stuff actually gives rise to a common sorting algorithm, which is known as heap sort. And basically, it is as common sense as possible. Basically, what you do is just repeatedly pop off the minimum. You get the smallest value, which is going to be -2. Well, we know it takes log n time to fix this, and so it'll fix it like this. We promote the smaller, which is 0. We'd promote the smaller one, which is the 1, and then we have the 10. So we pop again here. We would take off the 0, and then we would reprocess this. We promote the 1, we promote the 5, and the 13 comes up. And I'll just do one more iteration here. If you pop off the minimum, which is 1, and we repromote like this, we get the 2, we get the 3, and we get the 8. Notice here, basically you are roughly n times, because there's n elements, doing a pop, which is going to take log n time. You're going to get a sorting algorithm that has O of n log n time. You're just repeatedly extracting the minimum, but you're doing this in a very efficient way. And so this is actually one of the best sorting algorithms. It has a time complexity of big O of n times log n, which is actually extremely good. And there's actually a way to do this in a space complexity of big O of 1, which basically just means you're again rearranging the elements in that array representation. You're just moving them around in place, although the one we're going to code is actually going to have O of n space, which is basically what we're doing here, which is kind of making space for a new array and inserting them in order. The only other thing is to build the heap would be calling Heapify, which we saw at the beginning. And now I'd like to go over what Heapify is and how we can get a time complexity of it for actually just O of n. Okay, so this is currently a binary tree, but it's not yet a min heap. So to make it a min heap, we are going to call the function called Heapify, and we're going to precisely explain what that process is. So here is Heapify. Basically, you would start at this node right here because it is not a leaf, so we ignore the leaves for now. And this one's on the very far right side. So we start at him and we do an operation called sift down, which basically just means you push it down into its correct location. So we take 2 and we see, do we want to swap it with either of its children? Well, we're building a min heap, and so we want smaller values on the top. So we'd put the smallest of these 3 values right here, and so we want to swap it with the smallest, which is 1. We just sifted this 2 down into its correct position. Now we go over to this position here, the 10, and we sift it down. We see that the smallest of these 3 values is going to be the -4, so we are going to swap those 2. Okay, now we see the 3, we see that it's smaller than the 7, which is good, but it is bigger than the 2, so we would want to swap those 2 together. And the 5 here, well, it's actually equal to this 5 over here, and it's smaller than the 8. So we're actually totally happy with this 5. If you wanted, you could swap these, although of course it would do absolutely nothing. Okay, then we would would go over here and we see the -7. Well, that actually is the smallest of these three values here. And so it actually is in its correct placement for now. Okay, same thing with the -10. That is actually smaller than both of its children, so we're happy with where it is. Then we go up to the root here and we have a lot of sifting down to do for this 12 here. So the smallest of these three is going to be the -10, and that's how we get that root node of the smallest value there. We keep sifting this down here. We would promote the smaller of the two children, and here we would promote again the smallest of those three things, and we get it organized like this. So we can see that this is a min heap. Let's just go through in order here. The leaves are all fine. If we check the 1, well, it's smaller than both of these two. The -4 is smaller than 1 and 10. 3 is smaller than 12 and 7, and 5 is smaller than 8 and tied with 5. We go up to the -7, that is smaller than -4 and smaller than 1. 2 is smaller than 5 and 3, and we get the smallest value of -10 at the very top. It actually turns out that it is going to be on the order of just O of n to build this heap, which is tremendously useful and an extremely profound part of computer science. You can check out the proof if you want, although I'm definitely not going to go through it. The time complexity of this operation is going to be big O of n, and it actually can do it in place in the array by just adjusting the array positions, and the space complexity of this is going to just be O of 1 or constant. Now all of this stuff is going to be essentially the exact same for a max heap. Let me just show you a max heap. We could have 5 at the top with its children of 3 and 2, and 3 that'll be bigger than 1 and 0, and 2 is bigger than -1 and -5 here. Okay, so this is a max heap because for any node it is going to be bigger than its two children, and we have the very max at the very top. If you were to extract from this, basically you would be extract maximum or heap pop. You would take the bigger of these ones and you would promote like this. They're all going to be exactly the same operations, just for a max heap. Now something else that most people probably wouldn't show you, but they're kind of cheating you by not doing this, is that heaps are very, very useful in practice by putting tuples, or basically sequences of values, on the heap. So let's say that we had person A and they had the highest priority of 1. We had person B, they had the second highest priority of 2. Person C has 3, person D has 4, person E has 5, and so on. Okay, so what you could do to actually store this basically key value pair on the heap, you would put the number first because you want them sorted by the priority. So the number goes first, and then you could also store them on there as well. So you could actually make it look like this. We'll have 1 and A, we'll have 2 and B. So as you can see, we're basically rearranging a min heap here where it is sorting them by this first position, and then this is just the data that's getting stored on it. And so this is really, really useful because basically what you would do is you would pop this off, you'd have the actual data associated with that, and again in log n time you could basically promote these up like this, and this is like truly a proper priority queue because based off of priority you are actually popping off the data that you're interested in. So that's going to come up a lot in LeetCode problems, and I'll show you how to code that as well. Okay, so let's start with min heaps. So to build a min heap, we will use the Heapify function, and it's actually able to do this in a time complexity of big O of n, and the space complexity, if you are heapifying a array that already exists, then it actually can do that in constant space by just rearranging the elements in place. Okay, so let's say we had an array which was essentially representing a tree. This currently is not sorted, and it definitely does not satisfy the heap property, except you could make it satisfy the heap property by using the Heapq library. So if we import Heapq, then we can build the heap with heapq.heapify the array of A. We just use this library and call this function Heapify, and you give that our array. It's actually going to arrange that into a way that represents a heap. And so the -4 actually turns out to still be the root because it's the smallest value. So notice that this is still not sorted. Okay, it's not actually ascending totally. Okay, so one of the main operations we do with a heap is called heap push, which essentially just means inserting an element into the heap, and the time complexity of that is going to take big O of log n time to restructure the tree. Okay, so if we run heapq dot, notice the p's here, heap push, there's a double p, we give it the array of A and the number of 4. So again, a reminder, A essentially is our heap now. Originally it was just an array that's representing a binary tree, but it basically is our heap now. We're going to see that it actually shows up at the end. end. This actually kind of looks like it's in the wrong spot, but if you were to visualize it, it actually ends up looking like this, with -4 as the root, then 0 and 1, and 4 is actually the child of 2 here. And so this definitely does satisfy the heap property. Okay, one of the other main operations we do with the heap is called heap pop, and that is essentially just extracting the minimum value. So we take the minimum value out of that tree. And again, the time complexity of that to fix the tree is going to have just big O of log base 2 of n time complexity. Okay, so you'd write this as you'd get the minimum element is equal to heapq dot heap pop from the heap of A, and we'll output A and the minimum. We'll see that our array now doesn't have -4 in it. We take out that root, and it restructures itself to look like this. And this is our -4 that we popped off. Okay, now most of these functions have been using the Heapq library, and so you could write this all from scratch, although it's really complicated. We're just going to write one thing from scratch, which isn't very complicated, which is called a heap sort. So to do heap sort, well, it basically just sorts the array by popping from the heap repeatedly. So this has a time complexity of, among the best sorting algorithms, n times log base 2 of n. It has a space complexity of big O of n, except that's just the one that we're going to write. There's actually a way of writing it that's a little more complicated that is O of 1. So our version is O of n, but I'll just write a note here. Constant space is possible via swapping, but this is rather complex to do. Okay, so to define a heap sort, well, it basically takes an array. So notice I'm writing array as in it's not necessarily a heap already. It's just some sort of array of, say, numbers. And so the first thing we're going to do with it is heapify it. So we'll heapq.heapify the array, and now that rearranges the array so that it satisfies the heap property. We'll get the number of elements n is equal to the length of that array, and then we'll make a new list, which is ultimately what we're going to return. It's going to be the sorted list. This is just going to be a bunch of empty stuff for now. So we'll just write the list of 0 times n, so the indices of 0 to n minus 1, all filled with zeros. So then we'll go for I in the range of n, so we'll go through all of its valid indice positions, and we'll just get the minimum is equal to the heapq.heap pop from the array, or from the heap. So that gets the current minimum in log time, and then we just set new list at that index of I equal to the minimum. So this just repeatedly gets the smallest minimum at the time and places it at that position in the array. This is going to make the array just be in ascending order, and ultimately we'll just return our new list. Okay, so if we were to run heap sort here, we'll just give it a new array, which is not sorted and also does not have the heap property. So if we run heap sort on just some random array of numbers here, well, then that is going to return us the completely sorted array. So notice it's not just that it's satisfying the heap property, it is particularly in sorted order. And so it does this in n log n time. At the beginning, the heap has n things in it, and so it's basically doing n times a log n operation, and so that ultimately gets you a n log n time. Now the solution does have O of n space. We are actually making a new array. You could change its positions in place by basically swapping with the end, but it's a little bit more complex, and this is totally fine for learning. Now there's also something called heap push pop. This basically just pushes and then pops. So heap push pop, that's going to take a time complexity of big O of log n, because basically it's just 2 times log n. You just push and then you pop. So if we give it our old heap of A, let's just remind ourselves what that is here. If you are to heapq.heap push pop, notice the P's there, there's a lot of them. You would have to give that some element you want to push in, let's say 99. If we run that, we'll see that it pushes in 99, and it also popped off the root of 0. Okay, so that's how to work with a min heap. And to work with a max heap, what I wish it was is just kind of in Heapify, I wish it was something like this, where it's like type is equal to, max heap. We could just kind of change it to max heap. Unfortunately, that is really not the case. Heapq actually only supports a minimum heap, and so it's always going to make a min heap no matter what you do. But we can easily make it a max heap by just negating the values. So to make a max heap, we'll get that same array as before, and we'll just get n is equal to the length of b, and then for I in the range of n, before you do any of the heap stuff, you would want to do b at I is equal to the negative version of b at I. So now they're just all multiplied by -1, and now if you call heapq.heapify with b after that, if we output b, we're going to see, well, most of the stuff is negative now. So 12 was actually our biggest value, and so 12 is now ending up at the top. And we also had that 9 and 10 are very big, and they're also ending up near the top. Okay, so it's a little bit weird, and I'd say a little bit clunky. But what you would do is largest is equal to the negative dot heap pop from B. And if you output largest, well then there you go. That is it functioning as a max heap. This basically turns Heapq to force it to act like a max heap. So since we negated them, the biggest value of 12 is actually going to be the smallest negative value. So even though this is still acting as a min heap, it's basically now able to function as a max heap after we just negate the value when it comes out. And if you wanted to push into the max heap, heapq.heap push onto the heap of B, you'd have to give it the opposite number of what you'd wanted. So if you wanted 7 to be in there in the max heap, well then that really means you'd want to put negative 7 in there. So I'll just write a note there. This inserts 7, so positive 7 into the max heap. If you put that in there, that's again going to sort that into the right spot. One other thing you might want to do, we'll do this with the min heap, is to peek at the minimum value without popping it off. So peek at min. This would have a time complexity of big O of 1 because all you're going to do is just A at 0. The minimum is always going to be the root, which is just going to be the array at the first position. So this is a very quick operation to just ask what the minimum is without actually restructuring the tree. You might want to do with the heap is basically build it up from scratch, as in don't use Heapify, just kind of go and build it over time. So let's say we had some array of values. We'll say C is just some array of values, -5, 4, 2, 1, 7, 0, 3. So what you would do is we'll just call it heap is equal to an empty array, and then we'll do for each object x in C, so each number in C, you would heapq.heap push onto the heap. You would give that the number x, and then if we're to kind of print the heap along the way here, you can see that over time we're pushing stuff in, and this would have a time complexity of big O of n log n because you're pushing in n things over time, and as the heap gets bigger and bigger, the heap's going to have close to n things in it, so it's essentially that you're doing an n times log n thing. But it's really important to understand that this is a slower time complexity than calling Heapify. Heapify can do this in O of n time, but there may be times to kind of go through this one at a time and push elements. And so if you do have to do that, then that's going to be an n log n. Okay, and I'll just kind of write a note here that this is something else you might want to do, which is check how many things the heap currently has in it. So if you are to just get length of heap, generally you would just do len in Python for pretty much everything. Len in Python is almost always a constant time solution, and so very quickly you can just ask how many things are in the heap at any point in time. Now here's something that's really important for elite code problems, which is putting tuples of items on the heap. So let's say we had some array of numbers. So if we were to output D, well, it's just going to be an array, but it's common to want to count the occurrences of elements. And if you've seen my hash map video, but don't worry if you haven't, from collections import counter, you can just make a counter is equal to a counter object that takes the array D. And if you were to output that, then it's basically just this dictionary that says, okay, for 5s, we have 4 of those. For the 4s, we have 3 of those. And regarding the 3s, we have 2 of those. So it's just getting the frequency of the occurrences here. We're saying we have 4 5s in here, 3 4s, and 2 3s. Note that the key is the element that we have, and the value is the frequency of that item. So if you loop through the counter, you would do for key and value, so k and v in the counter.items. If you were to do this, well, we could just print k and v for now. That's going to show you that we're just looking at the keys and values. So again, we have 4 5s, we have 3 4s, 2 3s. So then what we'll do is we'll start with an empty heap. So we'll just call it heap is equal to an empty array. Each time here, we will heapq.heap push onto the heap. We will give it the tuple where the first item is the frequency, which is the value, and then the second element is the key. So then if we do this, and if we output our heap at the end, we'll see that the smallest frequency shows up on the top. Okay, so when you put a tuple onto the heap, it's first going to sort itself by this, and then if there is any ties, so if we have the same frequency, it's then going to compare by this. Okay guys, as always, you can check the video description if you want to take and run this code yourself. I hope this was helpful. Drop a like if it was, and have a great day. Bye-bye.